Hello, it's Keith here, and this is lesson 32 of the simple series of my Z80 assembly programming tutorials. We're back on the MSX1 today, and we're looking at bitmap drawing and sprite drawing. We're simulating a sprite using the tile map here because it's convenient for getting lots of things on the screen. And as I always say, if you're a beginner, I think you can create a very nice game with just the tile map. Now, our previous example had a Chibiko bitmap, that's our mascot here, that could move around the screen, and the one we've got today is fairly similar in some ways, but we now have sprite clipping. So our tile map graphic can now go partially or even entirely off the screen. And if we keep pressing up here, you can see it comes back at the bottom. So we're clipping the sprite on all sides. So this is basically, something you could use in a game if you need graphics that go off and on the screen. So how are we doing this? Well, before we go into the details of how the code is working, we need to discuss the theory of it. So let's go over to our theatre screen and let's discuss what I refer to as the logical coordinates. Okay, now basically when I'm writing these tutorials, this example works in the same kind of way on all of the systems. A lot of the systems have a screen size of 256 by 192. Very nice screen size, especially for working in single byte coordinates. The problem is if our sprites can go partially or entirely off the screen, we need coordinates that are not visible. So we need a range of coordinates for the on-screen area and a range of coordinates for the off-screen area. So basically, so that I can still work within bytes, I use a logical coordinate system where 2 physical pixels equals 1 logical unit. So our 256 by 192 screen becomes a 128 by 96 screen. Now on this system we're creating the Chibiko bitmap out of tiles, so each tile is 8 by 8 pixels. That means it would be 4 by 4 logical units. So that's how I'm doing my calculations in this example. And to be honest, this logical unit system is what I use in all of my more advanced software because I find it works very well, and by working in logical units rather than pixels or bytes, it makes porting code far more easy. Okay, so that's our logical units. The next thing we need to discuss is the actual algorithm that I'm using for my sprite clipping. It's basically the same in every example, so I apologize if you're sick of hearing about it, because if you've watched all these tutorials, but I have to assume you haven't. I'm also sick of talking about it, but this is just what we have to do. Okay, so if you assume that is our screen area, and you assume that that is our sprite, there's our sprite, it's got a smiley face, well, slightly confused face maybe, anyway. So our sprite will move around the screen merrily as it goes, but then, oh dear, it's gone partially off the screen, and so now what we need to do is we need to change the actual area that we're going to draw of our bitmap. Now, our tile graphic, in today's case, is made up of numbered tiles, so the top corner will be 128, 129, 130, 131, then maybe 132, 133, and so on. So we're going to skip numbered tiles from the area that we're going to draw, and so if our sprite graphic goes off the top of the screen, we need to skip these tiles and we need to change the height to this bit here. We also need to change the drawing start to 0 because otherwise it would be negative, which we can't really do. If it goes over the bottom, we have a much easier time. We only need to change the height because of course we'll stop and we won't draw this bit as soon as we've drawn the entire height of the sprite. Left hand side, well, we might need to do two things in this case. We'll need to change the width, of course, we'll need to change the 0 as well, but we'll also need to skip the first tile or the first number of tiles from the graphic before we start drawing. However, after each line, we're going in a consecutive zigzag format, so left to right, top to bottom as we're drawing our tile graphic, but after each line we'll then need to skip the part for the next before we draw the next line. So drawing off the side a little bit different there. Different again slightly on the right hand side. We need to change our width again, change the width to this bit, and we need to skip a bit after each tile, but of course we're starting from the first tile, number 1 or number 128 or whatever our code is defined as. So we have to do things differently there as well. The tricky thing is, of course, is we want code that can cope with cases where we're off multiple sides at the same time. And as I often say, the fun fact is that the Chibiakuma's game could not do that. If you look very carefully at the levels where things would overlap the corners, the sprite would become corrupted because the code didn't work properly. However, hopefully today's code does work properly. I have got very slightly better at programming since then, so we've got some code that can do the job, hopefully. So we're going to look at it today. We're going to look at the new tile drawing routine, the sprite routine, if you can call it that. We're going to look at the cropping routine. We're not going to look at the joystick routine, and we're not going to look at the main loop because it's the same as the previous simple series bitmap examples. So please take a look at those if you need to know more. What we are going to look at though is we're going to look at double buffering. We're using 2 screen buffers here so that we can redraw the screen without any kind of flicker. So we will cover that as well. Okay, so let's make a start. So here is the start of our loop. We've got a clear screen routine, we've got a draw player routine, and a page flip routine. So let's quickly look at the page flip routine. Now basically the way we flip the screen buffer, the visible screen buffer, is we use register 2 of the VDP registers. Now if we go down to the bottom here for our initialization, somewhere we should see, where is it? There it is. So this is the pattern table address. This is basically the VRAM address of the, they call it the pattern table, but it's the tile map is what I would call it. And so we need to change those bits to change the VRAM table that is currently being used. Now we're going to use memory addresses 1800 and 1C00 as the two possible tile maps. Now our visible screen bank value in memory will contain either a 1 or a 0, but what we need to do is we need to set these two bits here to select the memory addresses 1800 or 1C00 for our VRAM bank that's currently visible. We send this to the VDP control port. We then send the register number 2 plus 128, the 128 being the basically the command to tell it we're setting a register, and we out that to the VDP control port as well. This sets the visible screen bank. We then here XOR the visible screen bank bit from between 1 and 0 here. Now this visible screen bank will be used by the commands that are actually setting the VDP buffer here. So what we're doing here is we are basically loading in a bit, the bit either 1 or 0 from visible screen bank, rotating it to the left twice, and then we are ORing in 1/8 here, and this is setting the tile map base in a HL pair. The H part will be that, as I say, 1800 or 1C00. The L part will be 0, and then we are here clearing the screen by writing a sequence of zeros, 32 times 24, that's the screen size in tiles. So that's just a clear screen routine using these two screen buffers. Now we will see the same kind of code again in our get VDP screen pos function. Where is it? This is selecting an X and Y position in tiles, and basically we are just loading in the visible screen bank as the base for the tile map here. So that's how we are selecting the VRAM destination in either of the two tile maps. And as I say, one tile map is being shown to the viewer while the other one is being drawn, and then we swap over, and then we swap over again, repeating. This means that we can move our character around the screen and take as long as we want about it, and we don't see any flicker. So that's something that's worth bearing in mind. Okay, now let's take a look at the do crop routine. Now before we look at the actual code of the do crop routine, we need to understand how we call it. So the draw player routine is what instigates the drawing of that Chibiko mascot to the screen. The Chibiko mascot is 48 by 48. Now that is 6 by 6 in tiles, but we are no longer working in tiles, we are now working in logical units. So our 48 by 48 bitmap is 24 by 24 logical units, and so we load that width and height into H and L. We load the first tile number into IY. Now the first tile number of the Chibiko graphic is number 128, and then what we do is we call the do crop routine. The do crop routine will set or clear the carry flag on completion, and if the carry flag is set, the graphic is entirely off the screen and we don't want to try and draw anything. So in that case we would return, otherwise we run fill area with tiles, and we'll look at that in just a moment. Now let's take a look at that do crop routine and let's see how it works. Now in the next routine we're going to be cropping our sprite, which we'll be considering as being this, and we're going to be considering its position and cropping it depending on each of the sides of the screen. Now at the very start we're setting a value called sprite h clip to 0, and this is the number of bytes to skip after each line is drawn. Now bytes is of course in this case numbered tiles, so in this case, some of the bit of the tiles need to be skipped after each line is drawn, and so we're starting by setting that to 0, being optimistic that we won't need to crop anything. Then we're setting DE to 0. This is a pair of temporary variables that are used for our calculations, and what we're going to do is we're going to crop the top of the sprite first, or consider cropping the top of the sprite I should say. So we're loading in the Y position from C, and we're subtracting V screen minimum Y. Now this is the minimum position that is visible on the screen. Now the first logical unit that is visible at the top of the screen is number 80, and the first logical unit on the left of the screen is 64. And that is what we're doing here. So by subtracting V screen minimum Y, we're effectively moving our sprite's position and converting closer to physical units. But if our sprite is somewhere like this, our Y position will have now gone negative. Now, if it hasn't gone negative, we can just skip over the next bit, but if it has, we're converting that back to a positive, and we're basically rounding up here into a number of tiles, because of course, although we are calculating in logical units, the final result has to be a number of tiles. So we're converting to tiles there, and we're comparing to the height of the graphic. And if we're basically cropping the entire height of the graphic, well, we want to give up at this point, so we jump to all off screen, and all off screen does is very simply it sets the carry and returns. So all off screen is just giving up. It's telling the calling routine there's nothing to do. But if there is something to do, we're storing the amount to remove from the top in E, and we're setting the Y position to 0 here. The C register is the Y position, and it's still in logical units, but we've now removed the minimum visible pixel position, so we're closer to an actual final value here. Now what we're doing is we're adding the height of the sprite, and we're subtracting the height of the screen. Now if this has gone negative, that means that the sprite is entirely on the screen, at least considering the bottom of the sprite, so it's not in a position like this. So we can, in that case, not do any more. But if it's not, then again, we need to actually remove something from the bottom. And so we're storing the amount to remove from the bottom in D, again, in a number of tiles. So 4 logical units per tile. So we're rounding up to a number of tiles here. Okay. So D and E now contain the amount to remove from the top and the bottom. So we're adding those two together. And if it's not 0, we're negating it, converting it to a negative value and adding it to L. L being the height of the sprite. We're effectively updating the height of the sprite, removing the amount to remove from the top and the bottom. Now, the only thing left to do is if we are off the top of the screen, we need to remove, maybe we need to remove Chibiko's head from the tile numbers that we're going to draw. So what we're doing here is we're loading the amount to remove from the top in A, and we're then converting the width of the sprite into a number of tiles per line. And then what we're going to do here is a very simple multiplication here. We're basically just doing a multiply where we are taking the number of tiles per line, and we're repeatedly adding that to IY, IY being the first tile number that we want to draw. So we're effectively skipping part of the sprite. Okay, so we've done that for the height of the sprite, the top and the bottom of the screen. We're now going to do it for the left and the right. So we clear DE back to 0 because that's our temporary variable. And then what we're going to do is basically the same thing for the left and the right. The algorithms are just slightly different, only very slightly though. So what we're doing here is we are loading in the X position, subtracting the minimum X, and again, if we have not gone off the screen, then we aren't in a position like this. Turn around. So there, that position would go negative, but that one would not. So that's what we're doing there. So again, we're converting that to a positive if it's partially off the screen, and we're now comparing it to the width, so in H. And again, if it's entirely off the screen, well, maybe the Y position was okay, but the X one is not. So in that case, we would give up. We're now storing the amount to remove from the left in E. We're zeroing the X position and updating the X position here. So B is now the updated X position. We then add the width of the sprite, subtract the width of the screen. If it's not caused an overflow, then we need to remove something from the right hand side. Again, checking if it's the entire width of the sprite. You know, maybe our sprite is somewhere like this. In that case, there's nothing to draw. So we are, in that case, jumping to all off screen. Otherwise, we're storing the amount to remove from the right in D. Okay, so we've got D and E as the amount to remove from the left and the right. Now what we're doing here is we're converting that to a number of tiles, and that's because if we need to remove anything from either the left or the right, we need to skip some tiles after each line, because remember we're drawing in a zigzag pattern. So we update, in that case, sprite H clip with a number of tiles to skip. We then convert that back to a number of logical units, because this routine runs in logical units until the very last in moment. So we're then adding the width in logical units and updating the width in logical units. So we've effectively subtracted anything we need to skip in logical units. Okay. Now the last thing we're going to do here is we are going to skip any bytes on the left hand side. If we think about Chibiko mascot here, the little fireball here is on the left. Well, if that's the first tile and we're there, we need to skip that, and that's what we're doing here. So we're taking the amount to remove from the left in E, converting it to a number of tiles by doing 2 shifts to the right, and we're adding it to IY, IY being the starting tile number. So maybe we've skipped a tile or two there. Okay. Now the last thing this routine does is finally converts those logical units into physical tiles, which is effectively a division by 4 logical units per tile. So we're doing some shifts to the right here, dividing the X and Y position into tiles and dividing the width and the height into tiles. Final thing to do, clear the carry, and we do that by ORing A there. That's the end of the cropping routine for this system. The cropping routine is different for every system slightly here. Maybe you could argue it could have been better if the platform specific calculations were separate to the cropping. I have done that for a later tile map routine I'm going to cover, but as I say, this one, the cropping routine is slightly different to compensate for the limitations and capabilities of each system. Okay, so that's how we do our cropping. Once we've decided we need to draw a sprite, we run the fill area with tiles routine. Now, fill area with tiles is something we've seen in the past, but this version has been modified. So it's slightly different. It's somewhat similar, but it's slightly different. Now, basically, what we're doing here is we're calculating the last tile number horizontally and vertically that we want to draw to the screen here. And then what we're doing is we're calculating and selecting the VRAM destination of the first position on each line. So what we're basically going to do is we're going to draw our box Chibiko graphic. We're selecting a VRAM destination. We're then going to fill a line, move down a VRAM destination, fill a line, and keep doing that until we've filled our entire graphic. Exactly the same as before. As I say, it's just that things have changed a little bit with regards to the registers we're using. We're using IY here as the tile number, and we are sending those tiles to the screen here repeatedly. So we're sequentially sending all of those tile numbers to the VRAM until we've done an entire line. Once we've done a line, what we need to do now is skip, potentially it could be 0, but we would need to skip any tiles because our sprite is off the left or the right hand side of the screen partially. So again, in a situation like that, we need to skip a few tiles before we draw each next line, and that's what this line here is doing. Then we're just increasing the Y position and checking if we've got to the last Y position, and we repeat until we have. So there we go. So there aren't so many changes to today's example. Most of the changes are the do crop routine itself and the stuff for the double buffer. Anyway, if you like what you've seen today, please like and subscribe as always. If you want to support my content, as the text says on it, you can support me on Patreon. We're going to be coming back to this kind of thing again later. I do have a tile map routine which does a common tile map in the same way in all of the systems. So if you like that kind of thing, if you want to see more, please stick around. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching and goodbye.